Ladies and gentlemen, after some minor technical difficulties, this is Felix von Leitner on Bignum Arithmetic. Give him a warm welcome.
Well, good morning. Thank you for coming in this large numbers at this time. Unfortunately, I have a new notebook, and although I tested it on a Beamer and the DGA how it works, the Beamer here doesn't like it, and now I have to use this Apple computer. Just kind of ironic. Okay, so I will be talking about Bignum Arithmetic today. Okay. So every one of you has probably used Bignum Arithmetic, and many of you hopefully wondered how it's actually done on the code level. How do you write code that works with big nums? And I will talk about that today. Usually when I say Bignum, I mean 1024 bits and up. I will not talk about how RSA works, or about how AES works, or what exponentiation is. I hope you know that. And the agenda will be, at first, how to represent big numbers in a computer, then how to add them, how to multiply them, and then the most important part for cryptography is how to operate on how to do modulo operations. So the first question is how to actually represent them in a computer, and the normal numbers are represented with 2's complement, so that if you subtract 1 from 0, you get all the bits set, and that's the representation for -1. And that works if you have all the numbers have the same length, because then you know which bit is the most significant bit. But big numbers can have varying length. If you add 2 big numbers, you get the bigger number, right? So this is dynamic, and this doesn't work out, so no one does it like that. The next idea would be to have COBOL-like arithmetic that was used for accounting, and they didn't use that for speed. They used it so that they wouldn't have rounding errors. So it works, but does not scale at all. So what everyone does is using absolute numbers and a sign bit and put that in a struct. So I have some examples for this. So usually you try to have an array of integers, unsigned integers, and have the biggest integer type you can have for each limb. And the idea behind that is that some algorithms, the important ones, don't scale linearly with the number of limbs. So if you do a multiplication, you get you have to do work to the square of the length number of limbs in the big num. So if you have smaller limbs in the big num, then you end up doing more multiplication. So you want to have this as big as possible. And the canonical biggest integer type on the machine that fits in a register is size t. So that's what I'm using here to describe this. The same basically for gcrypt, which is used by GNU-TLS. That's why I have it in the list here. You can see that the array is usually allocated on the heap. So you have some kind of bookkeeping stuff, how much you allocated, and GnuPG gcrypt has this flags thing, which is kind of funny because they write down if this is a secret number, and if it is, then before freeing they zero the space. And well, usually the accounting is more work than just zeroing everything, but you know. Another important big num library is GMP, and they do the same. So everyone does it like this. The first important thing you have to do with big num is adding them. That's one step in all the other algorithms, so this better be fast. And usually the first thing you notice is that if you add 2, you get carry, and it might be just 1 bit, but it's still you may need 1 more limb in the result than you had in the 2 sources. So the size of is not in bytes, but it is in limbs, right? So most CPUs, well, any CPU really has add with carry, but it's not so easy to get this instruction from a C compiler. So the trick you normally use is that you use the double length integer type, which is long, And you cast if you want to add two integers and want to have access to the carry information, then you cast one of the integers to long, and then take the upper half by, for example, shifting right. The problem is if you are on a 64-bit machine, then long is already 64-bit, right? So there is no C data type for 128-bit integers, which is a big issue if you want to implement Bignum code in C. So GCC has an extension that's called __int 128, but that's strictly GCC. Even compilers that claim to be GCC compatible, like the Intel C compiler, don't have this data type. So that's what my code uses right now, but I mean, all the examples I give in code will be in assuming 32 bits. So unsigned long in this case is the 64-bit type. So this is basic addition. You just go through all the limbs. One thing I skipped over previously, but which is kind of important, is that the order in which you put the limbs in the array. You could have the same as the bits inside one integer. You could have least significant bit first, or least significant limb first, or you could have the most important first. And it turns out to be much easier to have the least significant first, because addition and multiplication go from the least significant one to the bigger one, and the carrying works in that direction too, and the CPU prefetch works in that direction too. So usually it's a win to do it this way. If you have a smart compiler, it will understand that this shifting by 32 bits is not actually shifting, and most compilers do that. But I have some numbers later on how well compilers work compared to assembler implementations, and it's a mess. So issues with adding two bignums is, the first one is it's not parallelizable, because you have the carry between every two limbs. So most modern CPUs are superscalar, so they have more than one adder in the CPU. And if you add two numbers, and each add has to wait for the one before that, then basically you can use more than one addition unit at a time. So this is an issue. People have proposed to use some tricks, but most of them only apply to hardware. So people have, for example, on smart cards, you do Bignum Arithmetic in hardware, or you add some instructions to the hardware to help with it. And there are some addition circuits that have lazy carry propagation, so they try to tune the algorithms so that the part they need first is ready first, but the rest trickles down in the next cycles. But you can't really do that in general purpose CPUs, so I'm not going to go into that much. You can do that in software. People have tried, but it's not worth it. So one important thing is that you can use Bignum Arithmetic to learn more about your CPU than you ever wanted. And it turns out that, in addition, it's not the one adder that bottlenecks the operation, but it's the memory access, even if everything is in layer 1 cache. So then you can see that some CPUs are more suited to Bignum Arithmetic than others, and the most glaring example is the Pentium 4, because it has half a cycle for normal adds, but 8 cycles for an add with carry. And since you have carry in every step in Bignum adding, you can see that adding is really slow on Pentium 4. Same for multiply. I come to that later. Subtracting works the same. You can understand how that works. You have to figure out the signed bit first, but usually in cryptography you will have unsigned integers, big unsigned integers. So the case where a number can even be negative is only in intermediate results of bigger calculations. So in some cases you can actually skip this whole signed bit stuff, but no one actually does. In multiplication, so the easy method that everyone learned in high school is just, I tried to write it down here, the school method. You see that the result of the multiplication will have twice as many limbs as the source. So usually in crypto the source numbers are the same size, or even more probable is that they are also the same number. So in many cases you don't actually multiply, you square. I have a slide on that too. So this school method, everyone has learned it hopefully in school. It's the easiest one to implement. The problem is that the results of the multiplications have double width. So this CF thing, right? So C and F are already the biggest integer you can fit in a register, so C times F is a long. And if you add two of them, like for example in this column, you see the mouse? Okay. If you add two of them, it doesn't fit in a long anymore. Right? So there's no bigger data type than long. We already tried to choose the biggest one. So the question is, how do you do that? And the dirty C trick is to have two longs and then shift and add the carry yourself, and that's kind of messy. And it's really the stress test for the compiler, because in that case you don't have enough registers to hold everything in registers. So the compiler has to be smart enough to notice that the lower part of the one long is no longer used after that, and reuse that register for the other long, right? So if the compiler were really smart, it would work out, but in practice it doesn't. So also multiplication is quite costly, so it scales to O n squared in multiplications, and what looks even worse on paper is that you have 3 times n squared additions for all the carrying operations. And this is if the compiler understood what I meant and doesn't do any superfluous stuff, then it gets even worse. So this is really costly. Interestingly, if you implement this, it turns out the adds are free, because in the CPU you have pipelined multiplications and superscalar stuff, and during the wait for the multiplication to come back with the result, the adds from the previous round are done. So I noticed this when I decided to do the first step or to all the multiplications with SIMD instructions, so the vector instructions of modern CPUs, right? So I did that, and it turned out that it took even just the multiplication stuff without the carry reparation pass, or whether it's the same data, it was already slower than the whole school multiplication was before. And I was shocked at that. I didn't expect that. So welcome to modern CPUs. So I wrote this down. This is also true for non-vector code, obviously. So if you just do the multiplications and write them to another array, like in this case, it turns out that this is much slower than the routines in OpenSSL, and this is just the multiplication, right? And this the slowness comes from the write back to the temp array. So you see that in modern CPUs, what you learn as assembler hacker in school, or I don't know where you learn assembler these days, but if you learn assembler, they usually tell you that you should avoid jumps, conditional jumps, and you should try to keep stuff in registers. And it turns out that the only thing that's really relevant to getting good performance in modern CPUs is that you do as little memory accesses as possible. So it's really worthwhile to not write or read anything that you can avoid. And I have some statistics on that. So if you keep stuff in registers and you have one memory access can cost as much as 200 cycles, and that's from the layer 2 cache, that's not from the actual memory, that's even worse, right? So just so you see the order of magnitude we're talking about here. So 200 plus cycles if you access memory needlessly. And mispredicted conditional jumps, and everyone was whining about this when this number was published, on a Pentium 4 is like 20 cycles. And if you calculate the peak throughput of the CPU, then you can do lots of adds in parallel, and this ends up to be like 120 instructions potentially, right? But if you see the 200 cycles, that's a whole different game. So it turns out looking at jumps, it does help. So if you unroll loops, it does help, but the code in the loop also needs to be fetched. So modern processors have prefetching for this. So it's not as important that it was. Now we have like double data rate memory, but in some CPUs that are more memory throughput stuff, this is a real issue. So I decided early on that I wouldn't really unroll loops completely, because I thought, it's more important to have this small code in the end. Because you end up writing the significant routines in assembler anyway. So the major issue in assembler routines is that it's completely unreadable usually. So if you have to write unreadable code, you better keep it small, right? So that if someone wants to read it, they have some chance in hell. So multiplication, I told you that adding with carry can take up to 8 cycles. Compared to the 200 cycles, that's nothing, right? So you see the priorities shift a little when you look at the actual hardware. So the next attempt for multiplication would be basically the same school method, but you don't calculate one row, or you don't calculate one row, but you calculate by column. I think I have this. No, I show this thing again. So the school method basically goes through this row, and then goes through this row and adds it to the other row, and then does this. So you still have temp memory where you write the intermediate values, right? So the other method does it by columns. So the first thing you do is just calculate this CF, and you can keep that in register and write it to the result. And then you calculate CE, you keep it in the register, then you calculate BF and add it to the register, and then in the end you do the carry adjustment and write it out. So the only thing you read is you read these numbers. You read them more than once, but this is level 1 cache. That's not that bad. It's just one cycle penalty, right? So you do read these more than once, but this is only written linearly. This is called the combo multiplication. Well, actually, this is an in-between step. So the school method just calculates all the values, and it just showed you that that's really slow. So my intermediate method would be to calculate one row and write the results directly in the result array, and then use the second row, but don't write them anyway, but add them to the same thing. So you still have overlapping writes to this, but at least you don't have these temp rows, and that's a big win. But it's still, depending on the architecture, it might still be slower than doing the other thing, the combo multiplication, which is the next attempt. But it's promising to see if the number of limbs is small, then this method is really the fastest you can have. So I have this cycle count on my home AMD machine. I have some benchmarks later. So other ideas to speed this up. You could calculate if you have 1024 bits. You can say I have this many limbs, which is depending on the word size, say 32. And then you can say to add 32 numbers, you need at least the logarithm base 2 bits in each column to keep the carry. So you could say I reduce the word size of the intermediates and the limbs, so I have enough space to hold the carry without any additional variables. So people do that. This is the method of choice, actually, if you use floating point numbers. So people have been doing that, not many. I know one, DJ Bernstein, so he's like this assembler god in Bignum circles, but no one understands his code. I spent like half a year on it, and the only thing I really understood is that he's using like floating point numbers. The problem with floating point is that if you add 2, then you lose the extra precision, right? If it doesn't fit, then the precision is gone. The exponent will be adjusted, and all you have is the mantissa really. So the advantage of floating point is that there is instructions that do one multiply and one add in one round, and there usually are more units to do multiplication and adding in floating point than in integer in CPUs. So this can still be a win, but you have to do this limb reduction. So you have to know in advance how big your numbers will be, and then you reserve that many bits for the carry operation, and you end up needing more multiplications. So this is, if it's really worth it, I don't know. So Bernstein has some great numbers, but it's only for 512-bit numbers, in which case, you know, okay, no one really uses that anymore. So it might still be worth it to get the parallelism. On the other hand, it's really difficult to get the straight bits out of the floating point registers again after the operation. So this is worth it if you do many operations on the same numbers, which is coincidentally what you do in cryptography, because you do exponentiation, and that's basically a number of multiplications in a row. So this can still be worth it, but the jury is still out. I haven't actually implemented this. The current record holder for the fastest implementation is the combo multiplication, which is like the school method, but going by column. Comba is some Italian guy who had to write some embedded graphic stuff. He's virtually unknown, but Wikipedia has a page on him, so if you want to know. The idea is to do the rightmost column first, and then you have one linear write over the result set, result array, and that should be the fastest, but isn't on my AMD box. It is faster on Intel chips. So if you really want the best performance, you end up doing CPU ID in the beginning and then choosing the routine, which is kind of, well, it's a sad state of affairs, I think, but you know. So you can get really good performance out of this. So if you remember, I had 1,400 something cycles, and this implementation gets 900 something, which is a lot faster. But he did a massive unrolling, so he doesn't have any. He has a special case for 1024 bit times 1024 bits, and then he has completely unrolled the whole thing, and there's no loop counters anymore. So his code is like 300K for one multiplication. I wasn't willing to go that far. So there are some very interesting multiplication methods in the literature. The easiest one is the Karatsuba multiplication. This is an obscure Russian mathematician from the 40s who published this paper then. So the idea is to split the numbers in a low and a high part, and say you can reach both parts by the high part, but can you be shifted left? Yeah, it can be shifted right, and then you can just say these are two numbers, A and B. And so the paper uses decimal arithmetic, like 10 to the power of something, but in computers you would use 2 to the power of something, right? So you would split them in half, and then you can do some clever formula tricks, and then you end up reusing, like AC is used twice, right? So you get some more additions and subtractions, but you use, instead of 4 multiplications per round, you use just 3. So this looks great in academic papers, but if you implement it, it turns out to be slower. And that's because it's depending on the number of limbs until you have some break-even point. And that break-even point turns out to be 2048 bits on x86, and it might be even more for on 64-bit machines. And this is something you see a lot of times if you read papers off the internet, and then they say, wow, this is great, I have to try this. And then you spend like a week implementing this, and until you finally get it right, and then it's slower. So there's a generalization of Karatsuba, which is an n-part split, so the formula is even bigger. And you have more temp results, which I told you previously is evil. You don't want any temp results, because writing back to memory is the slow part. So this generalizes to a 3-part split, or n-part. You usually use 3 parts. It's even harder to implement. It looks even better. The coefficient in the paper, in the O big N notation, looks better, but it's even slower. So this doesn't pay off at all. And then there's the ultra version of the academic thing. It's an Fft multiplication, so you choose a slightly smaller limb size. This is done because it's implemented in floating point usually. So if you squint your eyes and you're under the influence of some drugs, if you see that it looks like a convolution, then you can apply a Fourier transform. And if you have done that, then you can multiply pairwise, which is wonderful because it's parallelizable perfectly, and the issue is unfortunately that the FFT is costly too, and you have to do it like 3 times, 1 for A, 1 for B, and 1 for the result. So it ends up being much slower unless you have like a million digits, and people use this method to calculate pi to great lengths. So GMP actually implements this, so if you want to see code for this, well. So I did some benchmarks. I have to say, in the announcement for the talk, I said this is my pet project to write code, and I'm not very far, I have to admit that. So what I did so far is addition and multiplication, and the modular stuff I haven't even really started, so I have some code, but it turns out my idea didn't work out, so I'm really at square one there. Anyway, so what I did to compare mostly is obviously the code I have myself, because I wanted to know if my code compares to the other code. And about a week ago, I got this new notebook here, and it's a Core 2 Duo. And this is something most assembly programmers will be familiar with, that you write this great assembly code and it outperforms everyone, and you put it on a different machine and then it's slower than everyone, right? So this is exactly what happened to me. You see that my addition code is the fastest of all. as long as you stay on AMD, and on Intel it's really slow. So you can also see that normal multiplication, like the schoolbook one and the comma multiplications are on AMD, the normal one is faster, but on Core Dual, the comma one is faster. So I was shocked by that really. And one thing that's really important to me is that you see how much variance you have between these cycle counts. So these numbers are not like seconds or time, but it's the CPU cycles. So if you have more gigahertz, then this number scales up, right? So this is independent of the actual CPU. If you know it's a power save mode or not, it's just the cycles. So this is only comparable, obviously, if the CPUs have about the same megahertz count. So you can see that the numbers are in the same ballpark usually, but gcrypt, which is used by GNU-TLS, is almost half an order of magnitude slower than the rest. And I didn't expect that. I thought, these people have been working on that for 10 years. It would be the fastest ever, and there is assembler code in there. It's not just C code. Then I would understand, right? But the people have spent time coding this in assembler, and it's slower than my C implementation. So that was kind of surprising. So you saw that these numbers, well, that's a lot. Like 1,500 cycles is a lot. But if you do it on 32-bit registers, where I told you need more multiplications, then it's twice on the same CPU, right? So the one was 64-bit code, the other was 32-bit code. It's just because the work is squared, right? It's O of n squared. So if you really want to have the biggest limb size you can have. So one other thing that I found very interesting is to see do you really need assembly code, or can you just write it in C and get a really good compiler? And so I tried various compilers. On 64-bit I only tried GCC. Well, I tried the others too, but they don't support the 128-bit integer type. So I couldn't compile my code with that. So apparently if you want to have 64-bit Bignum code, you have to use GCC or write in assembler. So you can see here that the gain by using assembly code is huge. It's like times 3 or 4, in some cases more, and in some CPUs it's so you can see that the Intel compiler is quite a bit better than the GCC, but still can hold a candle to assembly. Right, so I found that interesting, that there really are areas left where you can actually have significant performance increase by using assembler code. I thought those days were over, right? That's what you read in the papers. Anyway, one thing you have to do in Bignum cryptography all the time, the thing you really want to do is exponentiation. So the usual algorithm for that is that you have some temp number, which is the number you want, is the number you want to take the power of, and for each bit in the exponent, you keep squaring that number, and if the bit in the exponent is set, then you multiply it to the result. So that's basically the way you do exponentiation. The problem is in cryptography, you don't want the whole result. You just want to modulo some number. And I told you that writing to memory is the single slowest thing you can do. So this exponentiation algorithm works, but the result is huge. It's immense. You might have even a problem storing it in the first place. So this is immense. You don't want it. So, and if you got it, you would have to still take the modulo operation, which is a division that's much slower than multiplication even. Right, so this is a big problem, and it's an interesting change of mindset really, because normally you look at an algorithm and you see, how can I make this faster? How can I restate the problem to find a better way? And the cryptography is on purpose designed so there is no faster way. Right? They deliberately try to use the slowest operation they can find, so that it takes time to do it, right? Because the more time it takes to do, the more time it takes to try different keys. So this is an interesting concept to get your mind around. So if you look at this algorithm, you can see that at least half of the multiplications are just squaring. Right? You keep squaring the one number, and only if the bit is set, you multiply it in. And if you look at typical RSA certificates and implementations, you see that they usually use an exponent that's like 1 bit, then 31 bits of 0, and then another 1 bit. That's the usual exponent they use. And they do that on purpose too, because that was engineers, and they thought, well, if it has to be slow, let's try make it not that slow, right? So in the end, you keep up squaring all the time, and there's some normal multiplication in the middle, but that's it. Usually you are squaring. So the question appears, can you save more? Can you be more efficient if you know that you're squaring? And it turns out yes. So if you write this down, you see that you have this column in the middle of numbers squared, and okay, you need those. But the other is can be folded. So you have AC and CA. That's the same value, right? So you could save time. About 1/3 of the values don't have to be calculated. On the other hand, you still need the additions. And I told you earlier that the multiplications hide the additions. So if you do some clever stuff here to not do the multiplications, then you still have to do the additions that were hidden in the multiplication previously. Right? So in the end, this looks like it should speed up by 30%, but it doesn't. Also, there's additional bookkeeping needed. So about modular arithmetic. The public key crypto usually only works on residue classes, and it's modulo some big prime number. And it turns out you can use that fact. So you have to calculate the remainder after dividing by some really large prime number. And that's if it was a power of 2, it would be easy, right? Then you could just shift and it would be over. But that's we don't do that on purpose. So to give you an idea how bad division must be, I show you the latencies for multiplication. This is like on 64-bit machines. On Intel 64-bit, it's 12 cycles latency. On AMD, it's 5 cycles. And this Intel 64-bit, it's the new core architecture, right? So it's not the old crap. And still, the latency is much higher. And it turns out that multiplication is pipelined on Intel only in 32-bit, which is kind of... But division is not pipelined. So you can have more than one multiplication outstanding, but only one division. And division takes 161 cycles. So this is really bad, right? So if we have to avoid this, if at all possible. And it turns out... It turns out there are some tricks you can do. So the first trick that people thought of is to reduce the operands modulo the prime at every intermediate step. So the intermediate results don't get so big in the first place. Right? That's something you can do. For addition, that's easy. If you add two numbers and it's bigger than the prime. So the first thing you do is make sure that your operands are already reduced modulo the prime. So that's usually given in crypto. If you add two numbers and it's bigger than the prime, you just subtract it once and then you're done. For multiplication, it's a little trickier. You can reduce all intermediate values, which is a lot of bookkeeping again, and it's basically also division. The problem is that if we shift a column, I just wrote it in the school multiplication. If we shift left by 32 bits, it's free. In the normal world, but if you have modulo some prime, it's not free, right? We have to reduce the intermediate. That's expensive. So it turns out this is very inefficient, and there's some method to do it quickly, which is the Montgomery multiplication. So the algorithm is surprisingly simple if you look at it. So what it does, it doesn't calculate A times B modulo r, but it gives you A times B divided by 2 to the power of something modulo r, but it does that really fast. So the trick involved is that you get a different result, but to get that result back to what you actually wanted is cheaper than doing it right in the first place. So this algorithm is, in the end, you just have a loop that shifts all the time, and if the temp number is odd, then you add 1. So you know the lowest bit is 0 again, and then you can shift it out. Right? So this is deceptively easy. You can look it up. This works because you know that the prime you want to reduce by, the number you want to reduce by the modulo number is a prime, and that's co-prime to 2 to the power of something. So this is what the mathematical reason why this is allowed. So there's some trick to make this to make this understandable. I could explain it, but it took me like a week. So you should look it up if you really want to know why this is allowed. But Montgomery multiplication works. The problem is that you have to pre-calculate on the numbers you want to multiply, and you have to have some step after the actual multiplication. And added up, that's about the same cost as the multiplication in the first place. But we looked at the exponentiation, which is what we really want to do. And in that case, you can skip the end step and do the pre-calculation just once, and then you do lots of multiplications in the middle. And the trick to do that is that you multiply the two numbers you want to multiply by the inverse of what the wrong part of what the Montgomery stuff adds. And then it turns out that the result has the same offset again. So this is some neat trick you can do in this case. And that's why this is the method of choice, because what we really want to do is not multiply two arbitrary numbers, but we want to have an exponentiation and modulo something. Everyone is using Montgomery for that. So if you look at the algorithm, you see that there's lots of shifting involved, and shifting a big num is relatively easy and doesn't cost much, but still, if you want to implement this, there's one observation you can do, which is if you do this for one limb, like 32 bits, you shift and you add. You could save this and do this only on one register and have a separate register where you set the bit if you wanted to add and leave it 0 if you don't want to add, and then in the end multiply this number on the whole thing, which is a linear thing. You don't have to multiply it once. And this is a lot cheaper than just shifting this, but that's not implementation stuff. I haven't actually implemented Montgomery yet, but I haven't thought about it. So yeah, that's basically it. So in the end, it turns out that addition is not that important. If I had known that before, I wouldn't have spent so much time on it. And all the high-fangled crap like the Fft multiplication are really just worthless for usual applications. So I hope I gave you some insight. That's the last slide. So if you have any questions. Anyone? So if anyone wants to help, by the way, in the project, you're welcome. Just come to me and I don't know. Do we have a mic? Portable mic?
I'm screwed and I have to either wait till you wake up and turn it on or find another thread.
One question from me. The benchmarks for the core 2 using GCC. Did you actually compare the results when forcing the GCC to create Opteron optimized code?
Well, the problem is that the current best version of GCC doesn't have a target for core 2. Yes. There is SVN version, which core dumped on me, so I don't have a value for that.
Well, I'm actually asking because I did some low-level optimization for population count, and there's a multiplication in it. And interesting, using the Opteron optimization is approximately 20% faster than using the normal Pentium 4 optimization also, because GCC doesn't really keep the multiplication if it can, avoid it and replace it with shifts.
Yeah, but the shift stuff doesn't buy you anything in crypto, because you usually have big numbers that are generated by using random values. So they tend to be approximately 50% of the bit set in every word, so shifting doesn't cut it. But the GCC issue is mostly in 32-bit code. On 64-bit code, you can see that it is slower, but it's not that much slower. Right? It might even be faster in the add case than my assembler version. So the main issue why the compiler-generated code is so slow is just the register contention. So all this code was of course compiled with omit frame pointer, obviously, but still it needs one more register than you have if the compiler is not smart enough, and that's what happened.
I was just wondering.
Next hour switches to a new group of 10. So if you want to learn all the bridges in that pool, you need to keep on asking for many hours in a row.
Yeah, I was wondering what version of the GMP you actually use for the benchmarking.
Of what?
Which release of the GMP?
Of GMP, the current one, right?
4.1 or?
Yeah.
Yeah, are you aware that there's actually an optimized version for Core Duo which gives you a GMP bench of around 8400?
I didn't know that. Where did you get it?
It's external because, are you aware what Sage is? S-A-G-E?
Mm-hmm.
The Sage people work mostly on Mac OS X, and the guy who runs it, called William Stein, actually compiled the GMP on his Mac OS X box, and obviously it sucked because it used the generic C implementation plus Rosetta, so he had some guy actually, well, I don't know if you know Turbo and Grandund from the GMP mailing list, but getting patches in there is a tricky business. But the thing is that as you remarked, the Opteron hand-optimized assembly code in the GMP sucked.
It's not that bad. It's a
No, on the Core Duo because of the pipelining differences. And
Yeah.
actually somebody took the time, wrote a properly assembly-optimized version of that, and he gets more or less parity with an Opteron 146 in that range, so it's not too bad. But
yeah, but this is something I guess all assembly hackers have to go through every time a new architecture comes out, and you just have to look at the code again and try to optimize it. I mean, this is not just an issue for GMP; it's like the others too. Right?
I know, but I saw you use a Core Duo-based notebook. So.
Well, this is just to give you the numbers, to give you an idea that even if you think you have the fastest code and you have a different CPU, then it's suddenly the slowest code, which is bad.
Now, the other remark I wanted to make is obviously for crypto purposes, 2048 bits or something like that is large. Well, there's obviously lots of application in computer algebra where your lim length is practically in the hundreds of kilobytes. So having FFT and that kind of stuff. Actually,
Yeah, no, I didn't want to say that FFT is completely worthless. People use it for the pie crap mostly, but for crypto it doesn't buy you much.
Well, and the other thing is that there's two more libraries which do FFT really well. One is called Flint, and the other one is an implementation in Magma, the computer algebra system, which supposedly claims to be 3 times faster on the FFT for large cases than compared to the GMP. But
GMP is already pretty good, so I was surprised. I did some million digit thing, and it was like. Tuck.
No, I know, but. The upcoming GMP5 is going to do a couple things that are quite nice. I mean, obviously you only care about exponentiation because you do crypto stuff, but the modular P operation, well, it's something we should maybe more talk about.
So this is a very interesting topic. So in case some of you were looking for something to do in the next weeks, you're very welcome.
Okay, eine Frage. Muss man unbedingt die Montgomery Multiplication so machen, also Bit für Bit? Also ein anderer Weg wäre ja Montgomery Reduction und dann normale Multiplikation und dann einfach die Attribute immer wieder abschneiden. Das funktioniert eigentlich auch. Ich weiß nur nicht, ob es schneller ist. Also ich habe es mal den anderen Weg implementiert, weil dann brauchst du die Division nicht, sondern kannst einfach an den 32-Bit-Grenzen abschneiden.
Ja, die Division sparst du dir aber auch in dem anderen Fall. Also du hast halt den Post.
Naja, also was mich ein bisschen stört, ist dieses Bit für Bit multiplizieren.
Nee, das meinte ich ja, das musst du nicht machen. Du kannst auch jeweils ein Register vorberechnen.
Ja,
weil es ja immer auf dem untersten.
Und was ja bei RSA-Implementationen, also bei der Exponentiation noch viel spannender wird, ist dann das ganze Thema Additionsketten, Sliding Windows und so. Also dann wird es auch nochmal richtig spannend, wenn du es.
Das ist ein schönes Research-Thema, also da kann man viel Zeit mit verbringen.
Alles klar.
The MIT FFT project uses some very fancy meta programming techniques to avoid memory accesses because of the structure of the problem they're trying to solve. They also claim to be able to avoid the kinds of problems, portability problems that you talked about. With one CPU, you get good results, and with another, arbitrarily bad results. Have you? You talked specifically about just about multiplication and
Yes.
addition and such, but you're working, or you could perhaps conceivably be working in a larger algorithmic context. Perhaps such techniques might be useful to you too. Have you given that any kind of thought?
The problem with metaprogramming is that you still need a model for the CPU that you target. And they have the same issue. They don't have to touch the actual assembly code, but they have to touch the generator, which might be even worse. So the question is, do you really gain something? And I don't know that. So I looked at metaprogramming in a different context. So I haven't looked at it at all for arithmetic, but it might be worthwhile. So you could argue that this libtom crypt ultra unrolled thing is some kind of metaprogramming, because he obviously generated the code for that. So, but it's worth it apparently if you look at the numbers, but I haven't done it myself.
Have you checked the stability of the timing of the assembly code?
Yeah, this is like 10, 11 loops and taking the lowest one.
No, I'm more referring to guessing the arguments from the timing of the cryptography.
Oh, I took the same number, a fixed number for all of the benchmarks. Everyone is operating on the same data, so there's no...
One of the critical questions, you might remember it for a year or so ago about cache mismatching in hyperthreading, where you can start estimating the private keys when you snoop the cache on the second CPU in a hyperthreaded system, which resulted in some changes in the assembly, for example, in OpenSSL. Have you checked something like that so far?
So supposedly Montgomery multiplication helps against the sniffing attack, but I haven't looked at it yet.
Okay.
So that's what I read. I don't quite understand why it would, but...
Magic.
Yeah, well...
Maybe you SMS somewhere and it sends you back a bridge address. And maybe that's...
Okay, thanks for your attention.